Scientist is expected to have complete knowledge of a particular topic, first-hand knowledge. That's why people think he shouldn't write on a topic in which he is not a master. This is considered a matter of respect. But for now, I'm setting aside this respect issue. My excuse is that we have inherited a very strong desire for our ancestors to connect all knowledge in one place. The name universities itself indicates that from ancient times to now, the most important thing is to understand everything by combining it all. But in the last 100 years, knowledge has grown so much and in such different fields that now a strange problem has arisen. On one hand, it seems we can finally collect all knowledge, but on the other hand, it's become impossible for a single person to deeply understand everything beyond a small area. I see only one solution to this problem. Otherwise, our main goal will be lost forever, and that solution is that some people take the risk and try to connect different facts and theories. Even if their knowledge is incomplete or borrowed from others, there's also the risk of looking foolish, and this is my apology. The language problem is no small one either. One's own language fits like perfectly tailored clothes, and when it's not immediately available, feeling comfortable in another language is difficult. I thank Dr. Inkster from Trinity College Dublin, Dr. Patrick Brown from St Patrick's College Maynooth, and lastly Mr. S.C. Roberts. They worked very hard to fit this new garment, meaning the language, on me, and they had to work even harder when I stubbornly refused to change my original style. If anything of the original style remains, it's my fault, not theirs. Erwin Schrödinger, Dublin, September 1944. In Spinoza's Ethics, Part 4, Proposition 67, he says that a free man thinks least about death. His wisdom is in thinking about life, not death. This small book is made from a series of public lectures given by a theoretical physicist. There were about 400 people in the lectures, which didn't decrease much, even though they were told at the start that the topic is very difficult and the lectures won't be popular. But in it, the fascists' most terrifying weapon, mathematical deduction, meaning math-based reasoning, was almost not used. The reason isn't that the topic is so simple that math isn't needed, but that it's so complex that it can't be fully explained even with math. Another thing that drew people to the lectures was that the lecturer wanted to clarify the basic idea between biology and physics, so that both physicists and biologists could clearly understand it, because, despite so many different topics, the entire book has one main purpose. To make a small comment on a big and important question so that you all don't get confused. I'll briefly tell you the plan of my book first. That big and important question is, can we explain everything that happens in time and space inside living organisms with the help of physics and chemistry? The short answer in this book is that although today's physics and chemistry clearly can't explain it, we shouldn't doubt that in the future, physics and chemistry will explain it. This would be a very simple thing, if it just meant that what hasn't happened yet could happen in the future. But it means much more clearly than that. It means that the reason why it hasn't happened yet is also clear. Biology scientists, mainly geneticists, have done very smart work in the last 30-40 years. Because of their work, we now know quite a bit about the structure of living things and how they work. And now we also know exactly why today's physics and chemistry can't clearly explain what's happening inside a living organism. The way atoms are arranged in the most important parts of a living organism, and how they interact with each other, is completely different from all the arrangements that physics and chemistry scientists have researched so far. This difference can only be clearly understood by a physicist, because physicists know that the laws of physics and chemistry are statistical, meaning those laws explain everything in the language of averages or probabilities. If we look at it from a statistical point of view, the structure of important parts of living things is completely different from all the things that we physicists and chemists handle practically in the lab, or imagine while writing theory. so it's difficult to even think that the laws discovered so far in physics and chemistry would directly apply to a structure for which those laws weren't originally made. A non-physicist won't understand this statistical structure difference. Now I'll give an example, which I'll explain in detail later. The most important part of a living cell is the chromosome fibre, which we can call an aperiodic crystal. In physics, we've only studied periodic crystals so far. For a simple physicist, periodic crystals are also very interesting and complicated. In non-living nature, these are the strangest and most difficult structures that confuse us, but compared to aperiodic crystals, periodic crystals are boring and simple. This difference is exactly like a simple wallpaper, where the same pattern repeats over and over, and on the other side a masterpiece embroidery like Raphael's tapestry, where there's no boring repetition, but a beautiful, meaningful design. When I called the periodic crystal complicated, I said it only from a physicist's view. In organic chemistry, scientists studying more complex molecules have come quite close to that aperiodic crystal structure. I think that aperiodic crystal is the main base of the structure of living things, so it's no surprise that organic chemistry scientists have made very important contributions to understanding the problem of life, while physicists have contributed almost nothing so far. Now that I've told the main idea of my investigation, I'll tell my approach, meaning method. First, I'll think like a very simple physicist who knows only physics well and understands statistical methods too. Then he starts thinking about living things, meaning organisms, how they work, and then he honestly asks himself if the physics he's learned can tell anything helpful to understand this big question. Later it will turn out that yes, it can tell helpful things. Then in the next step, when he compares his theory to actual biological facts, he'll find that his thinking is mostly correct, but some corrections are needed. This way, we'll gradually get closer to the correct view, or at least the view that I think is correct. Even if I'm correct, I don't know if my method is the easiest and best or not, but this is my own way, and the simple physicist I'm talking about is myself. I couldn't find a better or clearer path for myself to find the solution to this problem.
A good way to understand the simple physicist's idea is to start with a strange and funny question. Why are atoms so small? Atoms are really very small. In daily life, even the smallest thing we handle has a huge number of atoms. An example is Lord Kelvin's. If you could mark the molecules in a glass of water and pour that glass into the entire ocean and mix it well, then, if you take a glass of water from any corner of the ocean, you'll find about 100 of your marked molecules in it. The size of an atom is about 1/5000th to 1/1000th of the wavelength of yellow light. This comparison is important because with a microscope we can see the smallest grain, which is roughly the size of that wavelength. But even in the smallest grain, clearly visible in a microscope, there are millions, meaning thousands of millions of atoms. So why are atoms so small? This is actually an indirect question. We're not really asking about the size of atoms, but why we people, meaning living beings, are so big. Atoms seem small because we use meters or yards for length. In atomic physics, angstrom is used for length, which is 1/10,000,000,000th part of a meter, meaning 0.001 meter. An atom's diameter is about 1 to 2 angstroms. We use meters or yards based on our body size. There's a famous story of an English king that when his advisors asked for a unit of length, he spread his arm and said, "Take the length from my chest to my fingertips." Whether the story is true or not is separate, but that king would naturally suggest a length that matches his body. A physicist also needs his suit made of 6 yards of cloth, not 65,000 million angstroms. So our original question actually becomes, why is our body so big compared to the size of atoms?
So our main question is, why does our brain and the sense organs have so many atoms? so that the physical changes in them can be clearly connected to our complicated thinking. After all, why isn't our brain or senses so sensitive that they can directly sense just one or a few atoms? The reason is that what we call thinking is an organised, orderly thing. And for this organised thinking to work, the things needed, meaning experiences and perceptions, should also be organised to some extent. From this, two things are clear. First, the physical structure of an organ like the brain should also be organised like thinking, meaning the events happening inside the brain have to follow physical laws very exactly. Second, if the signals the brain gets from outside are organised, only then can they become clear material for thinking, meaning the interactions between our body and the external environment should also follow physical laws exactly, at least to some extent. Now the question is, if an organism was made of just a few atoms and was very sensitive, sensing just one or a few atoms, could it fulfill all these conditions? The answer is no, because atoms always move very randomly, here and there, which is called heat motion. This random movement doesn't let atoms behave in an organised or ordered way. Whatever happens between a few atoms won't follow any clear law. Only when there are a lot of atoms together, statistical laws start working clearly. And as the number of atoms increases, the accuracy of these laws increases. In this way, the events that happen become organised and orderly. All the physics and chemistry laws that work in living organisms are of this statistical type. If we think of laws of another type, due to the constant heat motion of atoms, they could never work. Now I'll explain this with some examples. I'm selecting these examples randomly, out of thousands, just a few. Maybe these aren't even the best examples, but they'll make the point clear. This concept is very basic in modern physics and chemistry, like in biology, the concept that organisms are made of cells, or in astronomy, Newton's law, or in math, the sequence of numbers 1, 2, 3, 4 is basic. For someone hearing this for the first time, they won't get a full, deep understanding in the next few minutes, but they'll get some idea. This concept is taught in physics books under the name statistical thermodynamics, and it was created by famous scientists Ludwig Boltzmann and Willard Gibbs. If you fill a quartz tube with oxygen gas and place it in a magnetic field, the gas becomes magnetized. Magnetism comes into it. This magnetization happens because oxygen molecules are like small magnets, and in a magnetic field they align like a compass needle, become parallel. But this doesn't mean all molecules become exactly parallel. If you double the magnetic field, the magnetization of oxygen gas also doubles, and this proportionality continues up to very strong fields, meaning as you increase the field, magnetization increases. This is a clear example of a purely statistical law, meaning the magnetic field tries to align the molecules in one direction, but heat motion keeps turning those molecules randomly here and there, so only a slight majority of molecules are in a particular direction. Every single molecule keeps changing its direction over and over, but their average, because there are so many molecules, is in one direction. This was a very smart explanation given by French physicist P. Langevin. We can also confirm it in a way. If the slight magnetization observed is due to heat motion, then if you lower the temperature, heat motion decreases, and molecules will align more clearly due to the magnetic field. And from experiments, exactly that is found, meaning magnetization is inversely proportional to absolute temperature. This is called Curie's law. In modern labs, temperature can be lowered so much that heat motion becomes very low, and the alignment of molecules due to magnetic field becomes very clear. This state is called close to complete magnetization. In such a situation, magnetization doesn't increase as much when the field is increased as it did before. Instead, the speed of increase slows down and finally goes towards saturation. This is also confirmed from experiments. But this whole system is stable only because there are so many molecules. If there were fewer molecules, magnetization wouldn't be constant. Instead, it would keep changing randomly, because then the competition between heat motion and magnetic field would be clearly visible. If you fill the bottom part of a glass vessel with fog, meaning small water droplets, you'll see that the upper boundary of the fog slowly falls down. And this slow falling speed is fixed, which depends on the viscosity of air and the size and weight of droplets. But if you look at any one droplet with a microscope, you'll see that the droplet isn't falling straight down. It's moving very randomly, here and there. This random movement is called Brownian motion, but overall the droplets are falling straight down on average. These droplets aren't atoms, but they are so small and light that even the collision of one or a few molecules makes them move. That's why they bounce around and, due to gravity, only fall down on average. This example clearly shows that if our senses could directly feel just a few molecules, our experience would be so strange and confusing. Some bacteria and other very small organisms are quite affected by this Brownian motion. Their movement happens only due to the random heat motion of surrounding molecules. They have no choice. If they had even a little capacity to move themselves, they could go from one place to another, but it's quite difficult for them because the heat motion of molecules bounces them badly, like waves bounce a small boat in a rough sea. If you fill the bottom part of a glass vessel with fog, meaning small water droplets, you'll see that the upper boundary of the fog slowly falls down. And this slow falling speed is fixed, which depends on the viscosity of air and the size and weight of droplets. But if you look at any one droplet with a microscope, you'll see that the droplet isn't falling straight down. It's moving very randomly, here and there. This random movement is called Brownian motion, but overall the droplets are falling straight down on average. These droplets aren't atoms, but they are so small and light that even the collision of one or a few molecules makes them move. That's why they bounce around and, due to gravity, only fall down on average. This example clearly shows that if our senses could directly feel just a few molecules, our experience would be so strange and confusing. Some bacteria and other very small organisms are quite affected by this Brownian motion. Their movement happens only due to the random heat motion of surrounding molecules. They have no choice. If they had even a little capacity to move themselves, they could go from one place to another, but it's quite difficult for them because the heat motion of molecules bounces them badly, like waves bounce a small boat in a rough sea. Another example. This one is quite similar to the previous, but interesting. Physicists hang a very light object from a long and thin fiber to measure weak forces. These forces could be electric, magnetic, or gravitational, which turn this object slightly from its equilibrium position. This device is called a torsional balance. To increase its accuracy, physicists make the fiber as thin and long as possible, and the object as light as possible. But there's a limit when the hanging object becomes so light that the heat motion of surrounding molecules clearly affects it. Due to this, the object doesn't stay stable at its equilibrium position, but starts dancing randomly here and there, exactly like the droplets moved randomly in the previous example. This randomness sets a practical limit for measurement, meaning you can't accurately measure a very weak force, because the random collisions of molecules confuse the effect of the force. To overcome this problem, scientists repeat the same measurement over and over so that the effect of randomness is eliminated. This example is also important for our sense organs, because our sense organs are also a kind of instruments. It clearly shows that if our senses were very sensitive, they would become useless. Now I'll tell a very important quantitative, meaning numbers-based thing. From this, we'll know how much accuracy any physical law can have. It's called the root n law. Understand with an example. If, in some fixed conditions of a gas, there are exactly n molecules in one place, then in reality, if you check, there won't be exactly n, but a difference around n. If n equals 100 molecules, the error is about 10, meaning root 100, which is 10 molecules, meaning about 10% error. But if n equals 1 million molecules, the error is about 1,000, because root 1 million is 1000, meaning error only 0.1%. This rule applies almost everywhere where there are statistical things, meaning how accurate any law will be depends on the number of molecules involved in it. This is why living organisms should be quite big, because only then the number of molecules involved will be high, and laws can be accurate. If the muscles are few, accuracy will be low, and laws won't work clearly. This root n rule is a very strong condition, because 1 million molecules isn't too many either, if nature's laws have to be followed very accurately. So far, we've understood that a living organism, and all the biological processes in it, must be made of a very large number of atoms. And it's also necessary that random, meaning here and there events of just a few atoms, don't disturb the organism's work. According to a simple physicist, this is absolutely necessary, so that the organism has exact physical laws with which its system runs organized and perfect. Does this conclusion we have drawn from physics view match actual biology facts? At first glance, this conclusion may seem very obvious or simple. If there was a biologist from 30 years ago, he might say this is nothing new. Because an adult body, or even a single cell, is made of so many atoms that in every biological process, physical laws automatically become accurate. At that time, it seemed that these laws would always remain valid, because the number of atoms is very high, according to n law, but today, we know that this old thinking was wrong. Now we've learned that very small groups of atoms also control important functions of living organisms. These atoms are so few that accurate statistical laws can't even work in them. These small groups of atoms clearly control the organism's growth and its special features. And in all this, biological laws are very strict and clear. Now I'll give a short summary of biology, especially genetics knowledge. I don't have expert knowledge of it, so I apologize to biologists in advance that my summary is from a physicist's perspective. I'll only clear the main ideas because a physicist can't go into the full detail of biology experiments. In genetics, there are very complicated experiments, which include breeding and observing cells with microscope. Biologists mean by pattern the complete, four-dimensional pattern of an organism, meaning not just the structure of an adult organism, but the entire development from egg to adult is called pattern. This four-dimensional pattern is completely fixed by the structure of that one cell, meaning fertilized egg. And actually, this pattern is decided by the structure of a small part of the egg cell, the nucleus. In normal state, the nucleus is like a net, called chromatin. But when the cell divides by mitosis or meiosis, the nucleus clearly divides into some particles called chromosomes. Chromosomes are mostly rod or fiber-shaped. Their number is 8 or 12, in humans 48. Actually, these numbers are like 2 times 4, 2 times 6, or in humans, 2 times 24, meaning there are 2 sets of chromosomes. Both sets mostly look the same. One set comes from mother, meaning egg cell, and the other from father, meaning sperm cell. In these chromosomes, or in their center, the fiber, the entire future organism's pattern is stored in the form of a special code, script. Each set has the complete code. In fertilized egg, there are usually 2 such copies. Code script means that if there was a mind like Laplace's imaginary mind, who knew all causal relations clearly, he could look at the chromosome structure and say whether it will become a rooster, or a fly, or a maize plant, or flower, or mouse, or woman. The appearance of egg cells is often the same, and the difference in eggs like birds or reptiles' big eggs is only due to nutritional material. The code script is of the same type in both. Anyway, just code script word isn't right either, because these chromosomes not only plan, but also actually execute the organism's growth, meaning these chromosomes are both plan and builder at the same time. The growth of organism happens from repeated division of cells, called mitosis. Cell division doesn't happen as fast as we can think. Still, growth is quite fast in the beginning. Egg divides into 2 cells, then 4, then 8, then 16, 32, 64, like this. In just a few steps, many cells are made. If calculated at this rate, just 50 to 60 cell divisions are enough to make all the cells of an adult human body. Meaning, Every cell in our body is only the 50th or 60th generation of the fertilized egg. How do chromosomes behave in mitosis? They duplicate, meaning both chromosome sets duplicate to make two new sets. This process has been clearly studied with microscope. Every new daughter cell gets exactly the same two complete sets of chromosomes from the parent cell, meaning every body cell is exactly the same in terms of chromosomes. Having two copies of the complete code script in every cell is very important for organisms. Like in an army, a general tells his full plan to every soldier so that all work clearly. This analogy is exactly true in real biology. There's also an exception to this chromosome duplication, which we'll discuss now. Sometime after body growth, some cells are reserved for a special purpose, which later become gametes, meaning sperm or egg cells. In these reserved cells, mitosis happens very little. At maturity, meiosis happens, in which chromosomes don't double, but halve, meaning one daughter cell gets only one set of chromosomes. In humans, only 24 chromosomes, not 48. These half-chromosome cells are called haploid cells. Normal body cells are diploid. They have double set of chromosomes. In fertilization, two haploid gametes combine to make diploid fertilized egg again. In some organisms, fertilization doesn't happen after meiosis. Haploid cells directly grow to make complete organism, like male bee, meaning drone. Drones have no father because they are made directly from haploid egg. This is common in plants too. In moss plant, one generation is haploid and one is diploid. In animals and humans, haploid generation is very short. Only in the form of sperm and egg, our body is diploid generation.
In reproduction, the most important event is not fertilization, but meiosis. One set of chromosomes comes from father, one from mother. There's no role of luck or chance in this. Every person takes exactly half of their inheritance from mother and half from father. Sometimes one parent's qualities seem stronger, but the reason is different, which we'll understand later. The simplest example is sex. But if we look at grandparents' inheritance, the situation is different. I take the example of chromosomes I got from my father. Suppose I take chromosome number 5 from them. This chromosome is either an exact copy of my grandfather or my grandmother. This decision is completely 50-50 chance, which happened in my father's body in November 1886. It happened in meiosis. From that same meiosis a few days later, the sperm cell was made from which I was born. The same story applies to every chromosome from number 1, 2, 3 to 24. Whether mother's set or father's, these decisions are independent. Meaning, if chromosome number 5 came from grandfather, Joseph Schrödinger, chromosome number 7 still has 50-50 chance that it came from Joseph Schrödinger or from grandmother, Marie Bogner. But there's even more chance of mixing grandparents' inheritance in chromosomes. So far we thought that the whole chromosome comes either from grandfather or grandmother, meaning the chromosome transfers undivided, but actually it's not always so. In reductive division, meaning meiosis, before separating in my father's body, both copies of chromosome number 5 come close to each other. At this time, sometimes, those chromosomes exchange some parts. This process is called crossing over. Due to this, two qualities that were originally in one chromosome in grandchild separate, meaning one quality can come from grandfather and the other from grandmother. Crossing over is neither very rare nor very common, but due to it, we've got a lot of help in finding the location of properties in chromosomes. To fully understand crossing over, we need to understand some more biology terms like heterozygosity, dominance. This can't be given in detail in this book. Still, I'll explain the main point. If crossing over didn't happen, two properties of the same chromosome would always pass together, never separate. And if two properties are in different chromosomes, either they would be completely separate, or have a 50-50 chance of separating. But due to crossing over, this simple rule changes. If two properties are close to each other in the chromosome, their chance of separating and crossing over will be very low, because the chance of crossing over between both properties is low.
But if the properties are on both ends of the chromosome, they will separate in every crossing over. This way, we can find the relative position of properties in the chromosome. It has been estimated that mutation becomes a very rare event, because we've already seen that if mutations happened frequently, it would be harmful for evolution. In individuals where mutation makes the gene unstable, their next generations will have more mutations, and their survival chances will decrease. This way, unstable genes are removed, and only stable genes survive. But when we do breeding experiments ourselves and study mutations in lab, they don't have to be stable. These mutants haven't gone through natural selection, or if they have, nature would have rejected them because they were unstable. So if we see that such mutants mutate more compared to normal genes, it's no surprise. Now we can test our mutability formula, which was T equals tau times e to the power w over kt. Here T means expected time for mutation, and w is the threshold energy for mutation. Now we ask, if we change temperature T, how much does mutability change? If we increase temperature T by 10 degrees, T plus 10, the formula becomes T plus 10 over T equals e to the power minus 10w over kt squared. Here the exponent is negative, so this ratio will be less than 1, meaning when temperature increases, the expected time for mutation decreases, meaning mutation rate increases. This has been tested by scientists on Drosophila flies, and the result was interesting. In normal wild genes, the mutation rate clearly increased when temperature increased. But in already mutant and unstable genes, the mutation rate didn't increase as much. This is also expected from our formula. If W over Kt is large, which is necessary for stable genes, temperature change will have more effect. Now, how does mutation happen due to X-rays? This is also clear. We have already seen that mutation rate is exactly proportional to X-ray dosage, meaning a single event causes mutation, and mutation rate is only related to ionization, not to X-ray wavelength, meaning a single ionization event is responsible for mutation, which happens in a small place of just 10 atomic distances. According to our model, it's clear that this threshold energy comes from ionization. This ionization is like an explosion because one ionization event releases about 30 electron volts of large energy. This is not given directly by X-ray, but by an electron released from it. This suddenly increases heat motion a lot in the local area, like a heat wave. From this heat, 1 or 2 electron volts of threshold energy is obtained, which causes mutation. From this ionization explosion, not only orderly mutation happens, sometimes chromosome damage also happens. And this is more clear when we crossbreed damaged chromosome with another already damaged chromosome. This is completely expected and exactly happens in experiments. Another interesting thing is that in unstable mutants too, X-ray mutation rates don't increase much more than normal genes. This is because when 30 electron volts of high energy is coming from a single explosion, it doesn't make much difference in threshold of just 1 or 1.3 electron volts for mutation. Some mutations have been studied both ways, meaning from wild gene to mutant and from mutant back to wild gene. Sometimes mutation rate is same in both directions, sometimes different. This seemed confusing at first because threshold energy seems same both ways. But it's not necessary because threshold energy is measured from starting configuration's energy level, which can be different both ways. So this also matches our model. Overall, I think Delbruck's molecular model is quite accurate according to experiments, and we can confidently use it in future studies. I said earlier that from the molecular picture of a gene, it's clear that miniature genetic code can carry such a complicated developmental plan. But how does it work? How do we go from possible to understanding? Delbruck's molecular model doesn't give direct information about the detailed function of genes working, and I think physics won't directly explain this in future either. The answer can only be given by biochemistry and genetics, but still a general conclusion clearly comes from physics. And honestly, this conclusion was the main reason for writing this book. It is, living matter doesn't violate any known non-physics laws so far, but it must have some new physics laws that are still unknown. When those laws are discovered, they will also be a clear part of physics. This is a very subtle point, and in the remaining pages, I'll explain this point. Physics laws usually say that things in nature go from order to disorder. There's entropic principle. But life modifies this rule a bit. Gene stability is also due to this modified behavior. Living matter is not going toward entropy, but toward maintaining existing order. This is possible due to quantum physics. That's why life and living things show a special type of order that can't be understood just from general laws of entropy and disorder. But this order comes from maintaining pre-present order. This is my main conclusion that comes from Delbruck's molecular model. A living thing avoids dying because it doesn't quickly fall into that equilibrium state, which is the state of a dead or lifeless thing. This seems so strange that people from very old times have thought that surely some non-physical or supernatural force must be working in living things. Some people still think so. So how does a living thing avoid decaying? Simple answer is, it eats, drinks, breathes, or in plants' case, absorbs nutrients. In science, this process is called metabolism. In Greek language, it means change or exchange. But change or exchange of what? First, people thought it's just material change. But this is wrong because nitrogen, oxygen, or sulfur atoms are all the same. There's no benefit in changing them. Then, for some time, people said we live on energy. In some advanced countries, perhaps Germany or USA, restaurant menu cards also write the energy, meaning calories, of every dish. But this isn't exactly right either, because an adult human's energy is also fixed, and all calories are the same. So what is it in our food that keeps us alive? The answer is easy. In nature, whenever any process or event happens, entropy increases in that place where it's happening. Similarly, a living thing also constantly increases its entropy, and is going toward the maximum entropy state, where death happens. But how does it avoid increasing entropy? It constantly takes negative entropy from its surroundings so that it can stay alive. So actually, what an organism eats is negative entropy. Or in simple words, the main purpose of metabolism is that the organism keeps throwing its own produced entropy out into the environment. First, it's necessary to tell that entropy isn't some unclear or mysterious thing. It's a completely clear and measurable physical thing, like the length of a road, temperature of something, or melting point of a crystal. At absolute zero temperature, around negative 273 degrees Celsius, anything's entropy is zero. When you slowly supply heat to anything in reversible steps and take it to another state, even if that thing's physical or chemical nature changes or it breaks into different parts, entropy increases. To measure this entropy increase, divide every small portion of the heat you supplied slowly by absolute temperature. Then add all those small portions. For example, when you melt a solid, entropy increases this way. Entropy increase equals heat of fusion divided by melting point temperature. Entropy's unit is calorie divided by degree Celsius, like heat's unit is calorie, or length's unit is centimeter. I told this technical definition of entropy just so that it doesn't seem like a mysterious thing, but for us, more important is entropy's connection with statistical meaning, that physicists Boltzmann and Gibbs explained. That statistical connection is entropy equals K log D. Here K is a fixed constant named Boltzmann constant. Its value is 3.2983 times 10 to the power minus 24 calorie divided by degree Celsius. D is the measure of disorder. Explaining this D in simple language is very difficult, but this disorder is basically of two kinds. First, disorder of heat motion, random motion of atoms from heat. Different kinds of atoms or molecules mix randomly, like in the first example, sugar mixed slowly in water. The sugar-water example clearly shows, as sugar mixes equally in water slowly, D increases, so entropy also increases. Similarly, entropy increases from supplying heat too, because supplying heat increases atoms' motion, meaning capital D increases. And when you melt a crystal, It's clear that the ordered structure of solid is destroyed, and atoms move randomly, which increases entropy. If any system is isolated or environment is uniform, it increases entropy and quickly reaches that maximum entropy state, where everything is in disorder. This entropic law is just a natural rule in which everything is going toward disorder, like books in our library or papers on our table quickly go into disorder.
Now, in this statistical language, we can clearly tell the specialty of a living thing. The specialty of organism is that it stops entropy from becoming maximum. As I said earlier, it eats negative entropy. Or, clearly said, it continuously pulls order from environment toward itself to keep its entropy low. If D is disorder, then its reciprocal, 1 by D, is measure of order. Now, Boltzmann equation can also be written as negative entropy equals K log 1 by D, meaning negative entropy can be directly called order. So an organism continuously pulls order from environment to keep itself organized, meaning low entropy. This conclusion isn't as strange as it seemed at first. Perhaps it now seems a bit obvious too, because we clearly know that the order animals eat is in the form of complicated organic compounds, and after eating, this waste comes out in a low-order form which plants can reuse. For plants, this negative entropy mainly comes from sunlight. My physicist friends doubted the negative entropy thing. They said I could have used free energy, but I didn't because people get confused. A physicist, Simon, said that my negative entropy explanation doesn't clearly tell why we eat organic compounds. Why not eat charcoal or diamond? Simon is right, because coal or diamond reacting with oxygen also becomes a highly disordered state. But we can't live on CO2, so energy is actually important. So what I said in a funny way earlier isn't fully right. Energy is needed so that we can continuously remove heat and entropy from body. Perhaps that's why warm-blooded animals are more active. But I'm not sure how right this argument is. Simon, no. This is my own idea. Perhaps body temperature directly increases the speed of chemical reactions, which is a known fact. And I want to say that from what we've learned about living matter structure, it seems that living things work in a way that can't be understood from normal laws of simple physics. But this doesn't mean that some new force or supernatural thing is working which controls atoms in a living organism differently. The thing is that the construction of living things is different from any physical thing tested in labs so far. Like an engineer who only knows heat engines. When he sees an electric motor for the first time, he won't understand its working way. He'll see that copper, which he used to make kettles, is made into long wire coils here. Iron is also in coils instead of levers or cylinders. He'll understand that copper or iron is the same and same nature's laws apply to them. And this thinking is right too. But the difference in construction is enough that he gets a completely new kind of work. He can't think that electric motor runs from some ghost, just because it starts from a switch without steam. If a man never contradicts himself, it means he probably never says anything. The events in an organism's life cycle have so much regularity and orderliness that such a thing isn't found in any non-living matter. We learn that everything is controlled by a small group of atoms, which is very small compared to total atoms in every cell. And from the mechanism of mutation, we also understand that if just a few atoms in that group move here and there, the whole organism's hereditary features can change. These things are science's most interesting discovery. Perhaps these things don't seem strange to us because an organism concentrates a stream of order inside itself and avoids atomic disorder. Meaning, pulls order from environment to stay alive. All these things that happen in the structure of chromosome molecule are called a periodic solid. This solid gives a unique role to every atom, so it's more ordered than a simple periodic crystal. Notice that for physicists, this isn't just interesting but very exciting, because such a thing has never been seen before. It's generally believed that whatever order or regularity shows under physics laws, it happens only when the same atom configuration repeats over and over. Like in crystal, liquid, or gas, there are many same molecules. Whenever a chemist tests a complicated molecule in lab, he has many same molecules. Physics laws apply to them, like he can say that after 1 minute of reaction start, half molecules have reacted, and after 2 minutes, 3/4 will react. But about any one particular molecule, whether it will react or not, can't be predicted.
It's pure chance. As I told at the beginning about Brownian motion, a small particle's movement in liquid is completely irregular, but many particles together create a regular diffusion effect. We can also see a single radioactive atom's disintegration, but how long a single atom will live can't be predicted. We can just say that as long as the atom is alive, its chance of breaking in the next second is the same, no matter how many years have passed. This lack of predictability at individual level becomes exact law in large quantity, like exponential decay law of radioactive atoms group.
In biology, we see a completely different situation. Just one small group of atoms, which are in only one copy. They work in such orderly way that match each other perfectly, and also set perfectly according to environment. Later, when higher organism is made, copies increase. But how many? In an adult mammal, up to 10 to the power 14. Think, this is only the millionth part of the number of molecules in 1 cubic inch air. If all this come together in one place, just a very small drop of liquid would be made, and see how they are made in body. In every cell, only one, or in diploid, 2 on a work. And we know that in every isolated cell, how much power this small central office has. Doesn't it seem like small local government stations are set in the whole body, which easily communicate with each other because all have the same code? This may seem a bit poetic, but there's no fantasy in it, just simple scientific thinking. The things happening here, their regular and perfect order, isn't coming from some other physical probability mechanism, but from a completely new kind of mechanism. Observation is that guiding principle of every cell is in one atomic group, or sometimes 2, and it brings an order that is perfect, whether it seems strange to us or completely right. This situation is completely new. It doesn't occur anywhere except in living matter. Physicists or chemists studying inanimate matter have never seen such a thing that can be explained this way. So our theory doesn't cover this case either. That statistical theory, which we were very happy with because it showed how physical laws order is made even from atomic disorder, and the most general entropy law, can also be understood simply from molecular disorder. Life's order comes from a different place. It seems there can be 2 mechanisms for orderly events. One is statistical mechanism, which makes order from disorder. Second is new mechanism, which makes order from order. The second principle seems simple, more natural. That's why physicists were also proud when they found statistical mechanism, because this happens in nature, and this explains natural events, especially irreversibility. But we shouldn't expect that the physics laws we've made from that will completely explain living matter's behaviour, because living things mostly run on order from order principle. To explain this, we'll have to go into a bit more detail and refine the thing said earlier, that every physical law is based on statistics. Saying this over and over may cause doubt, because many things also run on direct order from order principle and have nothing to do with statistics or molecular disorder, like order of solar system. Planets' movement all remain same for indefinite time. Today's position is directly connected to pyramid time's position. Historical eclipses can also be calculated, which match records too. This calculation isn't on statistics, but on Newton's universal gravity law. Max Planck has a small paper. In that too, this distinction is there. Order from order, and order from disorder. His object was to show that statistical laws which control large-scale events are made from dynamic laws of small-scale events. So it seems that the new principle, order from order, which we called the real clue to understand life, isn't completely new for physics. Planck had given it earlier. So it seems like the clue to understand life is that everything is running like a machine, like a clockwork, as said in Planck's paper. This isn't completely wrong, but before accepting it as complete truth, we should think carefully. Let's now look carefully at a real clock's motion. It's not just a simple mechanical thing. If clock was only mechanical, there would be no need for spring or winding. Start at once, and it would run forever. But real clock, without spring,
The pendulum stops after a few beats. Its mechanical energy becomes heat. This all happens at very complicated atom level. Physicist has to accept that the reverse process isn't completely impossible. A springless clock can suddenly start from its own cogwheels and environment's heat. Physicists would say the clock got a very strong Brownian motion. Now, whether we understand clock's motion as example of dynamical or statistical law depends on our perspective. If we call it dynamical, we focus only on its regular running, which is possible due to a small spring that removes small heat motion problems. But when we remember that without spring, clock slowly stops due to friction, we understand that this is also a statistical phenomenon.
Now, if we look at the whole situation, the simple case we discussed above is an example of many other things. Actually, everything that seems to ignore molecular statistics laws. Whatever clock works, made from real physical matter, not imagination clock, and pure clockwork. Chance element always remains. Even if it's very small, of chance a clock breaking is infinite small. But that possibility is always in background. Even when we look at celestial bodies' motion, irreversible frictional and thermal influences are found there too. Earth's rotation is slightly decreasing due to tidal friction due to the moon is also slightly going away from the Earth. This all happens because Earth is in a perfectly rigid sphere. Still, one thing seems clear, that physical clockworks clearly show order from order features. That's why physicists got excited when they saw this in living organisms. It seems there's something common in both. But we have to see what similarity is there. What is that special difference that makes biological case new and wonder? When does any physical system, meaning any group of atoms, show dynamical law or clockwork features in Planck's language? Quantum theory gives its short answer. It happens at absolute zero temperature. When temperature is near zero, molecular disorder doesn't affect physical events. This isn't from theory, but from testing chemical reactions at every temperature, extrapolating them to zero temperature, which is actually never achieved. This is called Nernst's heat theorem, or sometimes third law of thermodynamics. First is energy principle, second is entropy principle. Quantum theory also gave scientific base to Nernst's law and also tells how close to zero a system has to be taken so that its behaviour becomes completely dynamical in every case. Zero doesn't always mean very low temperature. Nernst's discovery happened because at room temperature too, entropy's role is very low in many chemical reactions. Here, remember that entropy is direct measure of molecular disorder, its logarithm not. If we talk about pendulum clock, from above room temperature is almost like zero. That's why it works dynamically. If you cool it more and remove all oil, it will still run the same. But if you hit it more than room temperature, after some time it will melt, everything stop running. This may seem easy, but actually this is the main point. Clock works because they are Mabelin's solid which due to strong binding forces stay in their shape and avoid disorderly tendency of heat motion, at least at normal temperature. Now think a bit more. The similarity between clockwork and organism will be understood. Just simple thing. Organism also depends on a solid. Hereditary substances, aperiodic crystal, which mostly avoids disorder from heat, motion, but don't think that chromosome fibers are just like a machine's teeth, meaning cogs, at least without reference to that deep physical theory on which this example stands. And anyway, the fundamental difference between both is very deep, and that's why calling biological case new and wonder is right. After such a long scientific explanation, now I want to tell my one personal, a bit subjective thinking, which is connected to the philosophy of this whole discussion. The space-time events inside a living being's body, which are connected to its mind's activity, self-consciousness, or any action, looking at their complex structure, physiochemistries, statistical explanation, if not completely, strictly deterministic, then also statistico-deterministic for sure. I want to tell physicists that, in my opinion, and contrary to some people's thinking, quantum indeterminacy has no special role in a living system, biologically, just perhaps some accidental events like meiosis, natural, and X-ray induced mutation have a bit effect, but this is obvious anyway, and everyone accepts. Let's assume it's a fact, like I think most biologists also accept, just they have a strange feeling calling themselves just a mechanism, because it seems contrary to free will idea which we directly feel inside. But the real thing is that direct experiences, no matter how different, can't logically contradict each other.
So let's think what right, non-contradictory conclusion can be drawn from these 2 points. My body runs like a pure mechanism, follows nature's laws. Second, still from my direct experience, I know that I myself direct my body's motions, can understand their effects beforehand, and when those effects are important, I feel full responsibility for it. In my opinion, there's only one conclusion from this, that I, meaning I, which every human feels for himself, meaning every, that conscious mind, whoever said I or felt is that person. If there's anyone who controls atoms' motion according to laws of nature.
In our society, some ideas have been made a bit small or meaning changed, so this thinking may seem a bit bold. Said in Christian language, I am God Almighty. And see if this conclusion is the closest for biologist, from which he can prove God and immortality both at once. Actually, this insight isn't new. Its full record is at least 2,500 years old. In India's ancient Upanishad, the idea was Atma is Brahma, meaning personal self is universal, eternal self. From this thinking soon the idea of soul comes, as many bodies, as many souls, and then question rises, does soul die like body or can stay alive without body? First option seems boring, second option ignores the real thing on which this plurality thinking stands. And worse questions were asked, do animals also have souls? Sometimes it was even asked if only men have souls, or women too. From such things we understand that this plurality thinking, which is in all Western religious thinking, is a bit doubtful in itself. And if we leave their strange superstitions, but keep their simple idea that soul is plural, and improve that soul also ends with body, then we're doing even bigger foolishness. There's only one right alternative to this. Its plural has no meaning. There's only one thing, and whatever plurality shows is just different personality aspects of this one thing, which are made from an illusion. To stop our thinking, many ghost stories are sitting in mind, like it's said that a tree is outside my window, but I don't see the tree, some tricky way whose starting part only can be understood. Real tree sends its image in my consciousness, and I see that. If you stand near me and see the same tree puts its image in your consciousness too. I see my tree, you see yours, which is like my image, and what is real tree isn't known. This is all confusion, but if consciousness is accepted as one thing, then simple thing is there's only one tree, and this image, all are stories. But we all have this strong feeling inside that our own experience and memory is a unit different from other human. If analysed carefully, this I is just a canvas on which all experiences and memories are collecting, and if thought carefully, real meaning of I is that ground in which all things are gathering. You go to another country, make new friends, live life with them same as with old friends. If thought carefully, remembering old life or not isn't that important. The boy of youth, who was I, you can remember in third person like feeling a novel's hero. But no break, no death came, and if some hypnotist erases your old memories completely, even then you won't say you died. In any case, your personal existence doesn't end and never will.